Okay, today we're going to talk about graphs of sine and cosine functions. So we want you to be able to sketch graphs of basic sine and cosine functions and use amplitude and period to help sketch graphs of more complicated sine and cosine functions. And then we want you to also be able to translate the graphs of sine and cosine. So let's first take a look at sine and cosine and see what their graphs look like. We know from our previous lessons that sine and cosine are periodic functions, meaning that they have a repeat, and we learned that the repeat value for these functions are every 2 pi. So if sine starts at 0, 0 and goes back and forth, and then at 2 pi, it's back at 0, okay? So it goes through this cycle and just keeps going and going and going and going, okay? So in every 2 pi it repeats. Now, it kind of gets a little complicated when you're looking at these graphs and you're saying, wow, these are numbers and pi kind of happens in between the numbers. But if you look at this as being 1, 2, 3, you see pi is really at 3.14. This is 4, and here we have 5 and 6, right? And 2 pi is at 6.28. So we see this would be 7. So it's just below 6.5. And then putting those same numbers on the vertical axis, 1, 2, -1. Okay, so we see several things about the sine function when we do this. And I'm going to zoom in a little bit so we can just concentrate on sine. First of all, the domain is going to be all real numbers. Okay, so any number can be put into the sine function. Okay, and then we use the period to kind of help us determine where on the basic graph of sine from here back over to there it will be, right? Because if I put a negative number, it just means my graph is further this way. If I put a highly positive number, it means it's just further this way. But really this cycle of one period just keeps repeating, okay? My range is another thing that we notice. The basic graph of sine just goes from -1 to +1. It doesn't go any higher than that, okay? The other thing we want to notice is just the period, okay? And so we can see several things happening, and I've marked several important values here on our function. The first important value is 0, 0, okay? And another important value is pi 0 and 2 pi 0. So these are what we call my x-intercepts. Okay? So we notice that sine goes from being positive to being negative every interval of pi, right? Okay? So from 0 to pi it's positive, from pi to 2 pi it's negative. Okay? Now we also notice that it reaches its peak at pi over 2 for the top peak and 3 pi over 2 for the bottom peak. So that's where it's at its highest value of 1 and -1. Okay, so these are very important values for you to be able to memorize, and they correspond to the unit circle functions. And if we remember that these correspond to the y values of sine. Now let's take a look at these points because I'm saying pi and 2 pi. And what we're looking at this x-axis here, okay, and I need to be very clear about this because I sometimes take it for granted that you all know what I'm talking about, and then I realize that you don't, is this axis here is my theta axis, okay? It's not really my x-axis, it's my theta axis, right? And then this is my y-axis, right? Okay, so it's the value of my function. In fact, it would probably best be put as my f of theta axis. Okay, so the value of my function at a certain angle. Okay, so the value of, here's my angle axis, and here's the value of my function at a certain angle. Okay, now when we put that back to the unit circle, these y values here, or my f of theta values, correspond to the y values on the unit circle. Okay, So this is a different type of graph. It's a theta f of theta graph. Now let's go over to cosine. Cosine looks a lot like sine, actually. In fact, remember how we say that it's kind of sine of 90 minus theta equals cosine of theta, right? They kind of equal the same things, right? 90 degrees apart. Well, if you look at where sine starts here at 0, 0, and you were to try to identify that same point on the cosine curve, it would happen here at negative pi over 2 or negative 90 degrees. So yes, this point here, pi over 2, happens at 0 on cosine. This point here at pi happens at pi over 2. So the curves look identical. The values are identical. It's just they're kind of they're shifted 90 degrees on our theta axis. And remember, this is our theta axis, and this is our f of theta axis. Okay. Now, my domain for cosine is also all real numbers. My range is also -1 to +1. My period is also 2 pi. But the important numbers, the 5 important numbers that we see here on cosine, actually happen, the beginning of cosine is actually at 1, okay, 0, 1, and then we cross the x-axis at intervals of pi over 2, right? So we'll cross the x-axis at pi over 2 and then at 3 pi over 2, and we will have two sets of peaks, one at 0, one at 2 pi, and another valley, low valley at pi, which is -1, okay? So a little bit different from sine. But if you remember, cosine is the function that is even, right? We learned that in a previous lesson, which means we can fold it across the y-axis. And you can see here the symmetry with respect to the y-axis happening, okay? And you can see with sine the fact that it crosses through 0, 0, which means with its pattern not changing like that, that we have symmetry with respect to the origin. Okay. Now let's talk about the transformations of sine and cosine, and we're going to harken back to a video that we did in chapter 1 when we talked about transformations of functions. And this is just the same exact slide from that video where we have some function h of x, which is going to equal plus or minus a times f of plus or minus bx, plus or minus c, plus or minus d, right? Where a is going to control our vertical stretch or compression. And in trigonometric functions, we call that amplitude. And it's really easy to remember because this also starts with an a. Okay, so amplitude. And then b, so this is a, here was b. We know that's controlling horizontal stretch or compression. Okay? And in trigonometric functions, we call this period. So this number in front of the x controls how many cycles this function goes through and whether it's going to be greater or less than the parent function. Now c and d control horizontal shift and vertical shift, and that's not changing, okay? The only thing with horizontal shift is we sometimes call this phase shift. That's the only new term, but vertical shift might be also called translation. Okay, sometimes we use a lot of different words to describe the fact that we're just moving it up and down or sideways. Okay? So let's see what this looks like with our sine and cosine function, because it looks a little bit different from other functions that we've dealt with this same concept on. So when we are doing transformations of sine and cosine, a will always happen right before the sign, okay? It'll either be positive or negative, right? If a is positive, it's going to look like the basic sine function. If a is negative, it'll be, again, reflected over that x-axis, okay? If a is bigger than 1, we're going to have vertical stretching. If a is between 0 and 1, we will have vertical compression, okay? Now, b is going to be our period. Okay, this is how many cycles it's going to go through as compared to the parent function. And we're able to calculate that using the function 2 pi over b is going to equal our period. Now c is often given in terms of pi because theta is often graphed in radians. Okay, so remember our axes are theta and f of theta when we're graphing trigonometric functions. And then sometimes when we're looking at d, it's not always shown at the right-hand side of the function. Sometimes it's shown at the left-hand side of the function so that we don't get confused about what is actually in the actual sine function, okay? So don't be surprised if you see d out front. Just remember the difference between d and a. As a gets multiplied by the sine function, d is either added or subtracted to the sine function, okay? So now let's look at y equals 2 cosine of 3x. And I've got a couple different functions graphed here for you on Desmos. The first function here is my regular y equals cosine of x function. And you can see it's symmetrical with respect to the y-axis. We can fold it across the y-axis. But we've got a couple different things going on. First of all, we have our a here on our new function, which is the red function. So this is the y equals 2 cosine 3x function. This a, or my amplitude, is 2 times what it should be. And you can see this on the graph because my function actually has a new range of -2 to +2. Okay, so that's going to mean the range is twice as big as it normally would be. And then we've got our period. Remember we said period, or I like to make it the sign, the double-barred p, is equal to 2 pi over b, right? So in this case, we've got my period is 2 pi over 3. So every 2/3 pi, we're going to have a repeat, okay? So we see pi being right here on my graph. We see 2 pi being right here on my graph. 2 pi. Okay. So, and our repeat, because we're dealing with cosine, so our start is at the y-axis, here's our first repeat, here's our second repeat, here's our third repeat. So every 2 pi, we have 3 cosines. Now that is horizontal compression because we're doing more cycles, okay, than 3 times as many cycles as you would in a regular cosine function, okay? So we're compressing that. But it's really easy to see with these trigonometric functions. I almost wish that we would teach transformations of functions with trigonometric functions prior to the regular algebraic functions. But you can kind of see what's going on here more easily with trigonometric functions. Let's take a look at another function. Here we have y equals 3 sine of 2x plus pi minus 1, and I want you to list all the transformations from the regular parent function. Now the regular parent function, of course, is y equals sine of x. And here in the bluish purplish color, we have our transformed function, y equals 3 sine of 2x plus pi minus 1. Okay? So the first thing we see going on, our amplitude is going to be 3, right? Our period is going to be 2 pi over 2, right? Which is just going to be repeating every pi. Okay? And then we have a phase shift, which is horizontal translation of pi to the left, right? Because we're adding pi. And then we have horizontal shift oh, sorry, vertical shift, not horizontal shift. Vertical shift down. Down 1 for that -1, okay? So what that means for our amplitude is, though we go a total of 3 up and 3 down, okay, when we're looking at our -1 for our vertical shift, that's like saying my x-axis got moved down 1, okay? Or my theta axis, I should say, got moved down 1, okay? So you can see that's the middle of the function, okay? But really, my function's range and this vertical shift is what controls the range. Since it's -1, we're going from -4 to +2, okay? So that means my range goes from -4 to +2 inclusive, okay? My domain is still all real numbers, okay? And so that gives the full picture of how to actually graph this. And before we had things like Desmos and stuff that we can use to graph things really nicely, we actually had to use all these pieces of information to sketch graphs of these sine functions and cosine functions so that we could have a picture of what was going on with them. And we could mathematically show our graphs by plugging in the numbers into the functions, but being able to see, hey, this is my parent function, I'm just moving it down 1, moving it left pi, stretching it by 3, and I'm going to put 2 of the repeats in 2 pi instead of just 1. That was a key thing to be able to do for us, because it showed us then where our x-intercepts were, it showed us a lot of things, okay? So it made life a whole lot easier. So we've learned to sketch the graphs of basic sine and cosine functions. We've learned to use amplitude and period to help sketch graphs of sine and cosine functions. And we're sketching translations of the graphs of sine and cosine functions. And again, my main goal for you is to be able to know how to graph sine and cosine parent functions, know those 5 basic points that I talked about in the beginning of the video. And I'm not going to ask you to do anything more than basic transformations, you know, identifying the transformations, sketching them, not so much, because that's just a skill that's not really terribly useful, you know, but mainly being able to identify the transformations and knowing what they're doing to that function so that you know that, hey, I've graphed it properly. And I realize you're going to use graphing calculators to actually do the physical graphing of that. But be able to at least graph the parent functions on your own. Okay? So that's it for today.